and I'm going to talk to you about how to clean water polluted with heavy metals. So, why care about water? Well, it is our essential and vital resource, yet we often treat it as if it was unlimited. And there are, in fact, countries already experiencing water scarcity. Also because of misuse, past and present, which leads to pollution of the existing water sources. So how long are we going to turn a blind eye to the fact that what we take from nature we also need to give back? And how can we clean up our mess as efficiently as possible? So that's why I'm going to talk about new treatment method for water cleaning, which can generate a side product that can be further reused. And this product is called the Tufa. And Tufa is a type of limestone which forms at the surface from waters that are really rich in calcium carbonate, which is the type of waters that deposit lime scale on our kettles and washing machines and piping. And these are often found in limestone landscapes. Carbonate. So Tufa forms by a very simple process called precipitation. So when you have your water dissolving the limestone, it releases the calcium carbonate ions locked in the rock, and these move freely in the water. And as the water dissolves more and more, or it starts to evaporate, these ions get very concentrated to a level that the water cannot dissolve the limestone anymore, and the ions don't have any more energy to stay in solution and move freely. So they start to bond again into the calcium carbonate molecules. And these molecules join into crystals of a mineral called calcite, which is the main constituent of limestone. And these crystals are heavier and denser than water. So they fall out, they precipitate from the stream onto the stream bed and form a calcite layer. And if this happens over a sufficient period of time, this layer gets thicker and thicker until it forms a new rock body, which is called tufa. So we have waters, high in calcium carbonate, high in metals, but how do you get metals into the water? You see, it's a very straightforward and simple chemistry. It doesn't look like much excitement could be going on. But when you think about the water having all sorts of other stuff in it, besides this calcium carbonate, and it's moving, and these elements are not going to behave in a straightforward manner. They are going to mix and mingle. And this means that they can swap in chemical reactions. And this is due to due to two properties of atoms. First, this ionic radius, which is effectively the size of the atom. So if you've got two atoms of very similar or the same size, they can swap and another atom can get into the new substance. And the other one is electrical charge, which is determined by the number of electrons. So again, if you have two atoms of different elements with the same or very similar charge, they can just swap in the process. And this is called ion exchange. And as I just explained, when you have a metal that is of similar size or charge, it can just swap for calcium, and you form these other metal carbonate molecules. And these can then be incorporated in the calcite crystal alongside the more abundant calcium carbonate. And this way, these metal carbonates are removed from the water within the crystal. And because the crystals precipitate and sink from the water, taking these metals with them, we can refer to tufas as sinks for the heavy metals. So where do we get our water? In nature, you get them in limestone landscapes. You've got rainwater and surface water and groundwater infiltrating into the limestone. And this water is slightly acidic, which dissolves the calcium carbonate very easily. So the water becomes saturated with the dissolved limestone, and when it reaches the surface and the point of saturation, it starts precipitating the calcite. But Limestone is commonly used by humans in construction and industry, for example, for cement production. And all of this generates extensive amounts of waste, which contains the calcium carbonate and all other nasty stuff like heavy metals and other toxins. And this is often just dumped in the middle of a field or in a lake or a river, where it gets infiltrated by water and it dissolves the calcium carbonate very easily, and you already know the rest of this story. The water becomes saturated and you can start creating your tufa. But because the water dissolves all of the other nasty stuff, you've got heavy metals such as lead, zinc, copper, and nickel, which are in very high concentrations, orders of magnitude higher than you find in natural systems, which makes them toxic for living organisms, from microbes to plants and to humans. And I'm looking at one such site, which is a small pond outside Glasgow in the middle of moorlands. And it has a very turbid and obviously dirty water with no organisms living in it, no plants, which gives rise to the suspicion that it is just someone's waste that has been dumped there. And it is in sharp contrast to the moorland ponds around, which are natural and which have very clear water and thriving populations of all sorts of water creatures. And there has been tufa forming where the water flows out of the pond throughout the last 20 years, as you can see. So this is the cross-section of my site. And I took water samples from the pond and down the stream at regular intervals to see how the water chemistry changes. And the source water is very high in calcium carbonate and the heavy metals. Sorry. And what I expect to see is that the levels of the calcium carbonate and the metals would gradually decrease downstream as they are caught in the tufa. And if this proves right, we can develop this method further and implement it into other waters polluted with metals and rich in calcium carbonate, and use it as a natural way of water treatment. Obviously, you can have other wastewaters from other industries and mining, for example, which have very high content of heavy metals, but no calcium carbonate. And in this case, you can just add some extra material to give the water the chemistry necessary for tufa formation. There are obviously questions still to ask and answer because this is a very new field. So how stable are these tufas in the long term? There are other natural processes affecting them, and they can be dissolved partially if you have seasons of high rainfall. Therefore, the net amount of metals caught in the tufa is not the maximum that could be, and we need to see whether this net amount is actually worth using this method, whether it's going to be really effective or whether too much of the material is going to be released again. And then there's climate change. You get extreme weather events, you get acid rains, in which the tufa is going to be extremely vulnerable because, after all, it's a limestone. You can form it very easily, but it dissolves even more easily in acid. So why take this further? Well, first of all, it is a natural process, and you just turn your semi-liquid or liquid waste into solid rock. And there are other methods for water treatment using calcium carbonate, but these often produce amounts of semi-liquid waste sludge, which has to be dealt with separately. But if you turn it into the rock, you don't need to remove it in order to keep the process going. You just leave it there. Therefore, you don't need to remove any additional waste. Because it's so simple and easy to keep going, you don't need to build a new water treatment plant at the site. You can just set it up, and it requires very little supervision. You just come to monitor the water chemistry every now and then. And when the water loses enough calcium carbonate and cannot form more tufa, you can just stop the system and remove the rock so it doesn't get dissolved again naturally. You can just take it away and use it, for example, as building stone again. And what is very important, these tufas can form in a wide range of environments around the world, except for the driest, where you just don't have enough water to keep the system going continually, or in the wettest, where it would just dissolve in the amount of rain in Amazon rainforest, for example. But otherwise, these can form in many countries which already experience water scarcity. So just to sum up, that it is essential that in the demanding global, the increasing global demand for clean water, we clean the water that we polluted. And we can use this simple method, which uses very simple chemical reaction. We can use it for natural and man-made waters, and we can apply it worldwide. Thank you.
You talked about Tufa being a natural way to clean water, right? Would it be a very suitable way due to the increase of demand of water and how fast it needs to be cleaned? Would Tufa be a sustainable way to supply clean water to populations that need a drastic increase of water?
I think it would, because you get rid of the problems of waste removal as you have with industrial wastewater treatment. But the issue may be that because it's a natural process, it's not very rapid. Cleaning the whole water source would take years and years. So it largely depends on how much water you need at a certain time and on how long a time scale, whether it needs to support a very large population or whether it's a region where you don't have many people living, so they don't use that much water. So in that case, you can use some more long-term and slower way of treating water. But if you have some densely populated areas that are struggling strongly, you can use this, but you may need other methods alongside.
Okay, my question is, did the cleaner Tufa-treated water in Neilston show any new signs of life?
Not in the pond, because the pond is still the pictures you saw, it is still that brown, that dirty. But when you go downstream in the Tufa, and actually you reach a point where the Tufa ends, you can see that beyond that point, the stream is a lot cleaner, and there are plants living, and you get insects in there, so I believe that the Tufa takes out significant amount of pollutants to make the water safe for the environment again.
I have one more question. Somebody's asked, how did you select your study site? How did you know about the site in Neilston? And did you work in a lab that does environmental testing for councils or something?
It wasn't as complex as that. Basically, our degree works in a way that in the final year, our lecturers present us with topics that they do research in, and they may propose some projects or let us propose a project. And I spoke to one of them, and he mentioned he knows about this Tufa and about the environmental connections. And I just thought, yeah, that sounds really good, because I'm from a country that has many places where tufas form naturally. So I was thinking, yeah, that may be something I may apply after uni when I come back home.
Hi, thanks for the great talk. I really have no knowledge of chemistry. It was such a long time ago. Now the tufa itself, is that because it's absorbing all the chemicals, as I rightly understood? Is that itself toxic or dangerous?
No, it's the water that contains them at first that is dangerous, because it gets into the ground and plants, and it is consumed by other organisms. It is toxic to them. But if you lock it into the rock, there are very little organisms that would eat the rock. So, yeah, it is about taking the toxicity out of water, although it depends on how much of the toxic stuff gets into the rock, whether the rock may be toxic if you handle it somehow. And again, if you dissolve the rock that took out all the toxins, that water that dissolves it would be toxic again.
Very, very nice presentation. I wanted to ask, can this tufa have an impact in the metal and minerals resources in the industry, considering the fact that we're mining and using metals at an alarming rate, and we're looking for new sites to dig up. Many of these sites are in the forests and places that need to be protected. So by taking this tufa, can we at least try extracting most of the heavy metals that we pull out as waste and reusing those heavy metals instead of trying to look for new sites to dig into?
That is a very interesting question, actually. Thank you. I am not sure about this, but it would certainly be a way of extracting them. When the calcite precipitates, it's all like very small atomic molecular scale. So if you wanted to extract these metals, you would need to do a lot of chemistry for it. But there are the other ways of treating water, or like when you have ponds that gather waste from other industries, and these contain these metals as well, and are treated, and the metals are actually extracted from that waste. So I think it would be possible to try it with the tufas. Does that answer your question?
Yeah, it does.
Thank you very much.